So this week, we're going to start to study or review some of the things we've learned in previous math and physics classes. Particularly, I want to focus my attention to force vectors. Now, we've all heard of vectors before, so I don't think this will be a very complicated topic. But I do want all of us to be on the same page so that we can apply vectors to our study of statics. So I apologize in advance if it seems like we're spending too much time on what should be just a prerequisite. But from my previous experience, it may be helpful that we get a very good grasp of vectors, specifically force vectors, before we move into applying them into statics. So first off, what is a vector? You've learned from your physics classes that there are two types of values, right? Scalars and vectors. There are others as well, but those two are usually the ones that you will use in an introductory physics course. We say that scalars are physical quantities that have only magnitude, right? So when we talk about vectors, we want to talk about physical quantities that have a magnitude, but also a direction. So what counts as a vector? What physical quantities can we express as vectors? You'll notice that not all physical quantities can be viewed as vectors. So let's look at mass, for example. Is mass a vector? Let's think about it. Mass has a magnitude, 2 kilograms, 5 kilograms, 10 kilograms. Does it have a direction? Now it doesn't. You may be confusing it with weight if you think it does, but actually mass does not have a direction, and therefore we cannot study mass as a vector. However, what happens if we multiply mass times gravitational acceleration, which has a direction and a magnitude? It becomes a vector, right? A vector that we call weight. And what is weight? Well, we know that weight is a force. So forces are vectors. They have magnitude and they have direction. And in this class, we will always treat forces as vectors. Let's look at another example. What about volume? Volume has a magnitude, right? 3 cubic meters, 5 cubic meters, 10 cubic meters. But does it have a direction? The answer is it doesn't, right? So volume cannot be treated as a vector. Instead, volume is a scalar. One more example before we move on. What about velocity? Velocity has a magnitude, 7 miles per hour, but also a direction. 7 miles per hour in one direction isn't the same as 7 miles per hour in another direction. So velocity is a vector, and its corresponding scalar quantity is speed. So when we look at speed, we think of magnitude but not direction, so we don't treat it as a vector. But when we think of velocity, we think of magnitude and direction. So we treat velocity as a vector. So vectors are physical quantities that have magnitude and also a direction. Probably the first step in analyzing a system will almost always be to determine which quantities are scalars and which quantities are vectors. So why do we need vectors? Why can't we just treat everything as scalars? Let's think of two forces acting on an object. We can say that the object is a hook, and that the forces are tensile forces coming from cables connected to the hook. So we have a hook. The hook is trying to lift an object. Let's say it's a box. From physics, you should know that the weight that the hook is overcoming is the weight of the box. However, how do we know what the hook is really experiencing? Think of it this way. If the cables are exerting a tension on the hook, then this tensile force, this tension, this force, can be modeled as a vector. Because the tensile forces acting on the hook will have a magnitude. The greater the box, or the heavier the box, the greater the magnitude of these two vectors. But they will also have a direction. Notice that one cable will exert a force in this direction. Another cable will exert the force in this direction. So we have two quantities that will have a magnitude and will have a direction. And just for the purposes of this exercise, I'm going to call them A and B. This little hat, this little arrow on top of the letter will denote our vector. So if you see this arrow on top of your variable, then we're talking about vectors. If you don't see it, then we're probably talking about their scalar quantities. So if we know that the hook experiences a vector A and a vector B, the question would be, what is the total value that the hook experiences? In other words, what is what we call the resultant? And in order to find the resultant, that is the total force that this hook is experiencing and the direction in which this total force is acting, we must first understand how to handle vector operations, or how to perform these vector operations. So let's focus our attention on our vector A. Vector A has a magnitude and has a direction. What happens if I multiply vector A by some sort of coefficient? For example, what if I want to draw the vector 2 times A? When you multiply a vector, then the vector will be scaled based on the coefficient that you used. In other words, if this is A, then 2 times A will be twice as big as A. So the coefficient will scale the magnitude of the vector, but it will not scale its direction, or it will not change its direction. So if vector A acts in this direction, then vector 2A will act in the same direction. It will just be twice as large as A. Now what happens if I multiply A by -1? You know that the coefficient scales the vector but doesn't change the direction. So A will be scaled at a scale factor of 1, which means that its magnitude will not change. But now look at this negative sign. The negative sign in the vector is going to change the direction into its opposite direction. So -1 times A will not change its magnitude. Magnitude will remain the same, but it will switch its direction. Now I want you to visualize vectors with coefficients and with negative signs as simply products. The vector 2a can be looked at as 2 times vector a. The vector negative a can be looked at as negative 1 times a. Looking at these vectors as if they were products will help us to understand how these coefficients actually affect the vector. Let's do one more. Let's say I want to draw the vector negative 0.5a. How would that vector negative 0.5a look? If you want to draw this vector, once again, I recommend that we look at it in terms of products. Negative 0.5a can be viewed as negative 1, that's what gives it its negative sign, times my coefficient of 0.5, that's what scales my vector, times my original vector. When I split this up into products, I can see that we have vector A. We are scaling it at half of its size, at 0.5. And we are changing its direction with this negative sign. So there we have vector negative 0.5a. And that's how vector operations work when we're dealing with products. But what about addition? When we are looking at addition, it's a little bit different. Because when we're looking at vector additions, we need to consider their direction. So let's do an easy vector addition. Let's look at two vectors. And I'm going to give them names of A and B as well. Let's say we have a vector A that is pointed in a horizontal direction. And let's say we have a vector B that is also pointed in the horizontal direction, but maybe with a different magnitude. If I want to find the resultant of vector A and B, then what can I do? I'm going to call this resultant vector C, and I can say vector C is the sum of A and B. Now, because these vectors are operating or are pointed at in the same direction, then all we have to do is add their magnitudes. In other words, vector C will be equal to vector A and vector B. And all of this will be equal to vector C. So vector C is one vector that starts at A and ends at B if we place them one right after the other. So vector addition is easy when vectors are pointed in the same direction, because all we're doing really is just adding their magnitudes, and then we end up with a vector in the same direction. But it becomes a little bit more complicated if my vector A and my vector B are not in the same direction. So what do we do when that happens? Suppose that I have a vector A that's pointed in one direction, a vector B that's pointed in a different direction. How could I add them? In this class, I would like to focus on two different ways of adding vectors that are in two different directions. The first one is going to be called the parallelogram law. Now, the parallelogram law is very helpful if our two vectors are acting or are starting from the same point. So what can we do? How can we find the resultant of A and B? How can we find this C, knowing that A plus B equals C? The parallelogram law tells us that we can form a parallelogram with our two vectors. In other words, we can take vector A and mirror it on the other side of vector B. So I'm going to take my vector A and I'm going to mirror vector A on the other side of vector B. Similarly, I can take my vector B and mirror it on the other side of vector A. So I'll have vector B, and I'll draw the same vector, but starting on the other side of vector A. So then what? What we end up with is a polygon with two sets of parallel sides. So a quadrilateral with two sets of parallel sides, which is what we call a parallelogram. Once we have the parallelogram, we just need to connect the ends of our two vectors where they are meeting. So the ends where A and B meet to the tips of where the two vectors meet. So we have end, we have tip, and this line that we draw that connects both of them is vector C. In this case, mathematically, this still looks the same. A plus B equals C. But we're not just adding magnitudes together this time. This time we're considering the magnitude as well as their directions. So, A plus B equals C, and this way of finding the resultant is known as the parallelogram law. We're looking at this from a very graphical point of view. Now the question would be, how can we then start to apply numbers to them? We're going to deal with numbers just in a second. Before we start that, let's look at another way of adding vectors. This is what's called the triangle rule. Now the triangle rule is helpful for when our vectors aren't acting on the same point, or from when we have multiple vectors. So what does the triangle rule tell us? If we have two vectors, A and B, and I'm just going to draw them here individually. We have vector A and vector B. Now the triangle rule asks us to start with one and add the other one. In other words, if I want to find A plus B using the triangle rule, I'll start with one vector. A plus B, I want to start with A. So I can draw my vector A here. And then to that, I will add my vector B. So when I add my vector B to A, I would just connect the end of B to the tip of A. So if I start my vector B at the tip of A, I have A plus B. Now to find the resultant vector, that is vector C, I just need to connect the end of my first vector to the tip of my second vector. And connecting these gives us vector C once again. So we're doing something very similar here, because notice that if you look at the parallelogram law, we have A, and this is a mirror of vector B. So the triangle rule is simply a smaller version of the parallelogram law, but a more generic version that helps us even when we're dealing with multiple vectors. Notice a couple of things. When you add numbers, it doesn't matter in which order you add them, right? 1 plus 2 is exactly the same as 2 plus 1. When it comes to vectors, the same rules apply. A plus B is exactly the same as B plus A. And how do we know this? we can look at the parallelogram law and the triangle rule. Notice that this version of the triangle rule, where I started with A and continued with B, is the same as the top portion of my parallelogram. A plus B equals C. But if I would have started with vector B, if I would have said B plus A equals C, then I would have had B plus A, and that will still equal C. So we have exactly the same answer without caring in which order we add these numbers. So the parallelogram law and the triangle rule are the two methods that we will use to add vectors. Now again, how do we go from this graphical form into an actually numbers-based method? We do this by applying geometry, trigonometry. And I'm going to be honest, I've noticed that geometry isn't really the strong suit of most of my students. So today, we're going to get a very, very quick but still detailed review of geometry. Suppose you have a triangle. Now, for the purposes of this class, we're going to identify angles with their opposing sides. In other words, we have a triangle, and I'm going to call their sides A, B, and C. And I'm going to call their corresponding angles little a, little b, and little c. So notice that the corresponding angle is the angle opposite to your side. That's how we're dealing with triangles, or that's how we're going to deal with triangles in the side. So we have a triangle, A, B, and C. There are two laws in geometry that relate these sides to their angles. And there's a lot of other theorems that we can use to find these angles. For example, if I say, what is the sum of the angles little a, little b, and little c? In other words, if I add up a plus b plus c, the angles, what would that add up to? I think all of you will be able to respond 180 degrees. Okay, good. So we know something about this triangle that helps us find these values. In other words, if we know two of these angles, we will know the third one. Right? I don't have to give you all three angles. As long as you know two, that's enough. But now there are two laws that will help us bring in the sides, the length of the sides, into our equations. The first one we're going to look at is called the cosine law. The cosine law says that the length of one side is equal to the square root of the sum of the squares of the length of the other sides minus twice the product of the lengths of the other sides times the cosine of its corresponding angle. So that is a cosine law. You've seen it before. But just in case you haven't, you know that this can actually be used to find the Pythagorean theorem. Now, we're all familiar with the Pythagorean theorem, right? A squared plus b squared equals c squared. But how can we relate that to the cosine law? Well, let's think. Let's say we have a triangle whose hypotenuse is C, and whose sides are A and B, and it's a right triangle. If we apply the cosine law to this right triangle, what do we get? We get that side C equals the square root of A squared plus B squared minus 2AB cosine of its opposite angle. And what is its opposite angle? 90 degrees. And what's the cosine of 90 degrees? 0. So we get that C is equal to the square root of A squared plus B squared. And this is the Pythagorean theorem. A squared plus B squared equals C squared. Square those two terms and you get the Pythagorean theorem. So the cosine law, even though you may not have used it before, you've still used at least a form of it, and you are familiar with the form of it. The second law that we're going to use to relate our geometries in terms of numbers is the sine law. Now the sine law tells us that the ratio of the length of a side to the sine of its corresponding angle is the same for all three combinations of sides and angles. In other words, side A over the sine of little a is equal to side B over the sine of little b, and it's also equal to side C over the sine of little c. Now these laws that relate sides to angles are going to be very helpful for us, because we will see that even with a limited amount of information of a triangle, we can solve for their sides and for their angles. So when we're using the parallelogram law or the triangle rule, we're going to be able to relate sides to angles, and this will help us deal with vectors. If we only cared about magnitudes, we wouldn't need these. But when we're talking about vectors, we also care about directions. And so if we care about directions, we need to know how to deal with angles as well as sides. So let's do an example. This is from your book. We're going to have an object experiencing tension from two cables. So we have a cable 1 and a cable 2. Now I'm going to say, and we're going to cover this later, but when you have cables, the tension that a cable exerts will always act in the direction of the cable. Okay, this is not something I want you to memorize now, but we will see this in the future when we're dealing with cables. So you have two cables that are pulling on this object. The first cable is pulling at an angle of 60 degrees from the horizontal. So if I were to express this cable or this force as a vector, it would be at an angle of 60 degrees. The second cable is pulling at an angle of 45 degrees. So we have two cables pulling on an object. Let's say that the first cable is exerting a force of 6 kilonewtons on this object, and the second cable is exerting a force of 2 kilonewtons on this object. So now my question to you would be, what is the magnitude of the resultant force from these two cables? And in which direction will that force act? The object is experiencing two forces that are pulling in different directions. So the result of these two forces is going to be one resultant force acting in one direction. Ideally, that direction will land somewhere in between these two vectors, but we don't know where exactly. And we cannot assume that it would be halfway. So how do we deal with this? We have an object. We have forces acting on the object. The best way to deal with this problem is to express our forces as if they were vectors. So we're going to have two vectors. My first vector will have a magnitude of 6 kilonewtons. Now don't be confused. When I say that the vector has a magnitude of 6 kilonewtons, I'm talking about the force itself, not the cable. The cable can be short, the cable can be long, but we don't care about the length of the cable right now. We only care about the magnitude of its force. So when I say 6 kilonewtons, and when I try to draw this vector at least somewhat to scale, remember that I'm talking about the force, not the physical cable itself. So we have a vector with a magnitude of 6 kilonewtons, And the direction is 60 degrees from the negative horizontal axis. And this direction will be important in just a second. We have another vector, a 2 kilonewton vector that is acting in a direction of about 45 degrees from the horizontal axis. So we have two different vectors. How can we find its resultant? We can turn to the parallelogram law, or we can turn to the triangle rule. For this example, let's use the triangle rule. I'm going to start with one vector, and I'm going to end with another vector. And for the purposes of this exercise, why don't I give them names? I'm going to call this vector A. I'm going to call this vector B. So now I can express this physical problem as a mathematical problem. And the mathematical problem is, what is A plus B? So let's find that A plus B using the triangle rule. The triangle rule says that A plus B should be equal to vector A and added to that vector B. So I'm going to start with my vector A. Vector A is a 6 kilonewton vector. And to that I want to add vector B. Remember, the end of B will be connected to the tip of A. And what else does the triangle rule say? The resultant vector is equal to the vector that starts at the end of A and ends at the tip of B. So my resultant vector will start at the end of A and will end at the tip of B. So now what does that give us? We have a vector A, which has a magnitude of 6 kilonewtons. We have our vector B, which has a magnitude of 2 kilonewtons. And adding them up, we'll have our vector C, which has a magnitude of, we don't know how many kilonewtons. Now, I mentioned earlier, directions are important, and we'll see why. In order to not make this diagram too confusing, I want to draw these a little bit bigger. There we go. So vector A, 6 kilonewtons. Vector B, 2 kilonewtons. What we have here is a triangle of vectors. Now notice that the sides of the triangle are equivalent to the magnitudes of the vector. So this side has a magnitude of 6. This side has a magnitude of 2. And this side will have a magnitude of, we don't know what yet. So how can we solve this? Let's apply the cosine law. But wait, to apply the cosine law, we first need to know our angles, right? So what do we know about this triangle? How can we relate this triangle to some directions? Notice that we have an angle of 60 degrees from the negative horizontal axis for vector A. That means that this angle is 60 degrees. But this actually isn't really an internal angle of my vector. We'll leave it there for now. Maybe it'll be useful to us in a second. Vector B acts at 45 degrees from the horizontal. But vector B is here. So vector B, even though it is not at the place it was in our diagram, its direction still doesn't change. Its direction is still the same, which is 45 degrees from the horizontal. So if I have vector B and I draw a horizontal line, then I can say that vector B is at 45 degrees from that horizontal line. And now what do you see? If we have two horizontal lines, so two parallel lines, then we know that this angle, which is 60 degrees, should be equal to this angle. So this angle from the horizontal line to my vector A is also 60 degrees. And now what does that tell us about the opposite or the corresponding angle to side C? The corresponding angle, which we call little c, is equal to this angle. In other words, 60 degrees plus 45 degrees. So we have an angle for this triangle. We have an internal angle of 105 degrees. Now we can apply the cosine law. You have it right there. I'm not going to write it again. The cosine law says that the length of side C is equal to the square root of a squared plus b squared minus 2 times a times b times cosine of C. In other words, the magnitude of vector C. Notice that I didn't draw an arrow because we're dealing with magnitude of vector C. We don't care about direction yet. So the magnitude of vector C is equal to the square root of a squared plus b squared minus 2 times a times b times cosine of the opposite angle C. You punch those numbers into your calculator and it should give you around 6.80 kilonewtons. It should actually give you 6.79 something, but it's going to round up to 6.80 kilonewtons. So we found the magnitude of the resultant vector. That means that this object is experiencing a force, a combined force of 6.8 kilonewtons. Is that everything we need to know to understand this object? No. In addition to understanding or knowing the magnitude of the force that's acting on it, we also want to know the direction of that force. In other words, we know that this side has a magnitude of 6.80, but now we want to know in which direction. Is it vertically down? Is it a little bit to the left? Is it closer to A? Is it closer to B? And we can find that using a little bit more geometry. So what do we know? We want to find the direction of this vector. In other words, if we measure the direction from the horizontal, which is what we will most likely be doing in this class, that means we want to find this angle. We have a couple of clues, right? We know that from the horizontal to vector A, we have 60 degrees. We know that there is an internal angle here, which corresponds to vector B. So I'm just going to call it little b. And we want to find the angle from the horizontal to vector C. So this angle, which I'm going to call theta, can be found by applying some of the things that we already know about angles. We have a horizontal line. So what is the angle from the beginning of the horizontal line to the other side of the horizontal line? It's just 180. Which means that if I add 60 plus my angle B plus my unknown angle theta, I should get 180 degrees. Now this makes our work a little bit easier to manage because notice that we know that one side is 60. We still need to find side B, but if we find side B, we should know what the angle theta is. So how can we find side B? We could try applying the cosine law again, but let's make things a little bit different. Let's use the sine law. The sine law says that the ratio of the sides of a triangle to the sine of its angle is the same for all three sides and angles, right? So which are our sides and which are our angles? We already have an angle here, 105, and we already have a side here, 6.8. So let's use C as one of our sides. So we say that 6.80 over sine of the angle, which is 105, should be equal to what? We want to find angle B. So if we want to find angle B, then we want to use its corresponding side of 2 kilonewtons. So we have 6.8 over sine of 105 is equal to 2 kilonewtons over the sine of our unknown angle B. And when we look at this equation, when we look at the sine law here, notice that we only have one unknown. So let's solve for that unknown. B should be equal to the inverse sine of 2 over 6.80 times sine of 105 degrees. And that gives us an angle of about 16.5 degrees. Now all that's left is to solve for our unknown angle theta. We know that theta plus b plus 60 equals 180, which means that theta should be equal to 180 minus 60 minus b, which is 16.5. That gives us an angle theta of about 103.5. But let's deal with consistent significant figures. We've been dealing with 3 significant figures throughout most of this problem. So if we want to express this in 3 significant figures, we can take it as 104 degrees. Now notice a couple of things. Rounding is important. And now you'll see why rounding is important. See, if we would not have rounded, and if we would not have applied our significant figures just yet, we would have actually ended up with 103.49. And 103.49 degrees actually rounds down to 103 degrees. Now, because the answers are so close to each other, it's not going to make too much of a difference for this analysis. But there was still a difference, even though it was small. So I want to encourage you to hold off on your rounding, hold off on your significant figures until the very end of your problem. For the purposes of the class, I'm not going to write all my digits, right? Because I don't want to overwhelm the board. But for your calculations, try to keep your numbers pretty much unrounded until the very end. So that's an example. We used the triangle law to relate or to find the resultant of 2 force vectors. We can use these laws to combine 2 vectors into one resultant. We can also use these laws to find the components of a resultant. So I know I said a couple of words here, so let's look at it in terms of our previous example. C is the resultant of A and B. So if C is the resultant of A and B, that means that A and B are components of C. So we know how to find resultants by using their components. But we can also find components by starting off with the resultant. Finding or dividing a vector into different components is what we call vector resolution. And we say that when we divide a vector into the components, we are resolving the vector. The components of a vector can be in the x and y axis, or they could be in an axis in any direction you want. If we have a vector, vector f, but I want to find the components of vector f along 2 axes that I'm going to call axis u and axis v, then I can resolve f into those 2 components, into components in those 2 directions, by essentially applying the parallelogram law in reverse. In other words, I can project my direction v until it meets with my direction u. And there I have my two components u and v. Typically, when our vectors are being expressed in components, we will write down the direction name as a subscript. So this component is f sub u. This component is f sub v. We can do the same thing on the other side. We can project our direction u until it meets with v. This gives us our two components, f sub v and f sub u. Parallelogram law in reverse. Before we finish today, let's look at one example of vector resolution. In other words, let's try a problem where we start off with a vector and we resolve it into different components. Now you guys are pros, so we're not going to do the x and y components just yet. We don't want to introduce trigonometry just yet. Instead, let's look at two arbitrary directions. So we're going to have an object, okay? Some sort of machinery. Let's suppose that these two objects are rigid. Do you remember what a rigid body was? We defined it as an object whose shape does not change, which means that these two bars are going to have a constant shape. They will be rigid. And suppose that I apply a force of 450 pounds at this point right here. So my force of 450 pounds is applied directly in the downward direction. Now there's a couple of things I know about this component, which I will give you so you can solve your problem. Let's say that the angle between this bar and the 450 pound force is 45 degrees. Obviously this is not drawn to scale. And let's also say that the angle between the two bars is 30 degrees. Now you'll quickly start to notice that unless we start identifying our members here, it's going to be very hard for us to actually perform our calculations. So I'm going to identify our members by identifying their ends. I'm going to call this my point A. I'm going to call this my point B. And I'm going to call this my point C. Therefore, this bar will be identified as AC. And this bar will be identified as AB. I'm going to write down their names here just for this particular problem. But in future problems, I'm not going to have to write their names because you will already know how to identify the bars based on the names of their ends. So now my question is, if I apply a force of 450 pounds, can I resolve it into components along the bars? In other words, can I split that force in order to figure out how much force is each bar experiencing? Now the answer is yes. We're going to use vector resolution. But before we even start or think about using vector resolution, we must first identify the directions that we're looking at. So in this coordinate system, what are we looking at? We want to resolve our 450 pound force into two forces acting, or two components acting along bars AB and AC. That means that our axis are going to be axis AB, which would be in this direction, and axis AC in this direction. The directions are very important. The directions are very important because they will help us identify where to draw our parallelogram. Now, there are two ways that we can work on this problem. We can just go with the parallelogram law in reverse, and then we can apply the triangle rule, so the sine and cosine law, in order to solve for our result vector. So let's do that. I have my 450-pound force, which is my resultant force. And I have my two directions, my direction AB and my direction AC. So what can I do? And I'm going to identify my directions here, AC, AB. So what can I do now? If I'm looking at the parallelogram law in reverse, notice that this looks a little bit different from here. And we'll see why in a second. I must first figure out where to draw my parallelogram. And this may take a bit of a trial and error in order to get used to. If we are resolving this 450-pound force along these two axes, the first thing we'll notice is that if we want to draw a parallelogram, our vectors may have conflicting directions. In other words, they may not always both act along the same direction. So then how can I do it? I can start, and this would be my first attempt, I can start by trying my parallelogram, trying to give it a side of AC, right? And then projecting AB on the end, on the tip of my parallelogram. So my AB will be projected here. Now remember, your parallelogram will connect where the two axes connect. So I have a component, an AC component, and another component which is an AB component. And now the question would be its directions. Remember something about the triangle rule. The triangle rule said that the resultant vector started at the end of one and ended at the tip of the other. Which means that if 450 is my resultant vector, it needs to start at the end of this component, which means that this component will move in this direction. It also needs to end at the tip of my second component, which means that the second component has a tip right here. So what we have is one component moving in this direction, one component moving in this direction, and the sum of the two components gives us our 450-pound force. I'm going to call these components FAC and FAB respectively. So now, do we have enough information to actually find those values? Because I see two unknowns there. Not sure if I can find those values. But remember one thing, we don't just care about the sides, we also care about the angles. So what can we say about the angles here? We know that the angle between AB and AC is 30 degrees. If the angle between AB and AC is 30 degrees, that means that the angle between the components along those lines is also 30 degrees, because force AB acts along line AB. Force AC acts along line AC. So if the angle between them is 30, then the angle between these two forces will also be 30. And what else do we know? We know that between line AB and my 450-pound force, I have an angle of 45 degrees. So I have my 450-pound force, and I have a force that acts along line AB. So we know that the angle between these two is 45 degrees. Therefore, this angle in the triangle will be 45 degrees. Now, is this enough to figure out the third angle? Yes. Remember, the angles in a triangle add up to 180, which means that this angle will be equal to 180 minus 45 minus 30 degrees, which is equal to 105 degrees. Okay, so we have our triangle. We have three angles on one side. Is that everything we need to calculate the remaining two sides? The answer is yes. In fact, we can calculate these two components by simply using the sine law. The sine law requires us to know one side and two angles in order to find the next side, or one angle and two sides in order to find the next angle. So if we apply the sine law, what do we have? We have our known values, 450 pounds divided by the sine of its corresponding opposite angle, so that would be 30 degrees. That's the corresponding angle. And this is equal to, let's pick an unknown side, let's say FAC. F of AC over the sine of its corresponding angle, which is 45 degrees. This is F of AC, this is 45 degrees. We can similarly write 450 pounds over sine of 30 is equal to FAB over the sine of its corresponding angle, which is 105 degrees. We can take both equations and solve for FAC and FAB respectively. This will give us a force FAC component of 636 pounds and a force component FAB of 869 pounds. Now here's something very interesting. If you look at this problem, you'll notice that 450 is the resultant. In other words, if you add FAB and FAC, you get 450. However, their magnitudes are greater. So what's going on? It's the directions. Because we are seeing a change in the overall direction, our resultant vector may actually be smaller, which is what we're seeing right here. Now, this is not a rule that applies to everything, which is why it's important to understand how directions work, and which is why it's important to be able to visualize vectors as triangles in order to apply geometry. So we've resolved this 450-pound vectors into a 636-pound force acting on AC and an 869-pound force acting on AB. And their directions tell us a little bit about how these forces are actually acting on these bars. We have a force on AC of 636 pounds in this direction. So if the force is in this direction, that means that my 450-pound force is actually pulling or exerting tension on this bar. Because force AB is in this direction, that means that my 450-pound force is actually pushing or compressing bar AB. We're going to talk more about tension and compression in following lessons. But for now, for this week, understand what vectors are, understand how we can express forces as vectors, and understand how we can use geometry to solve systems of forces.